as part of the course and as building up till tomorrow as well, we thought that as much as what you're doing, very mathematical study of regenerating codes in this case and so on, that it would be very useful to get your hands dirty, so to speak, and understand all the way down to the network. And when you talk about nodes and that you need to transfer some data from here to here, that what does that really mean? And is it as simple as just if you've got B bits that you can move it from one place to another, and what are all the other things that potentially you can consider? And later on, as we look at locality, what does that mean as well, and how do the codes necessarily need to change to do that, to handle that sort of thing? And it's kind of hard for me to actually to give to you something that I think is useful, to be honest, because I can see that you're all very thinking about mathematical codes and so on. So a lot of what I talk about is this sort of systems things, concepts and practical stuff. So I wasn't really sure what to put here. I had somebody sort of help me put a few things together. I kind of understand that that there's a few people maybe that haven't done any socket programming, that potentially haven't studied computer networks, but many of you probably have gone through some of those subjects. But we put some things in here, just some discussion. I think really the focus of this little topic is going to be is understanding some of the things that affect the throughput of the transferring of data between nodes, and what affects these things. And it's not just that you have k nodes and they're all the same, and you can make assumptions like that. So there'll be a bit of bandwidth and latency measurement at the end, maybe after the tea break. I'll come back and I'll run some commands where I'll connect to different nodes in Melbourne, and I'll use this node here in Camper, and we'll look at bandwidth and some other nodes, and we'll measure these things and just to see what we see. So all of these nodes, as you talk about, run on some kind of computer network, and your distributed storage system will run somehow over some sort of network like that, it can be very different depending on whether you're an organization that owns the entire network upon which all of your nodes are running on, in which case you potentially control a lot of the parameters. It's a local area network to you. Everything, there's a lot of things that can be homogeneous and it's much more controllable. Or whether you are outsourcing and you're running a distributed storage system over nodes provided by other suppliers, cloud suppliers and this kind of thing, in which case you don't have as much control. You might not know all of the things in the network underneath how it is working, because they just don't tell you all of the details of how things are working. And it may well be much more different as well if you consider very novel applications where maybe the nodes are on mobile devices, and you're trying to regenerate data across mobile devices as mobile devices fail or go away or something like that. I'm just trying to think out of the box that your distributed storage system, quote unquote, might not just be running here's on a cloud, and we run and we store some data and we access, but it could be something very novel. It could be something very different, and there you have to revisit your assumptions about what is the bandwidth that we have, and the latencies between nodes, and the failure rates, and all these kinds of things you might need to rethink, and then think about, if you saw these trade-offs in regenerating codes, well, where on that curve fits the kind of network that I have? This is a question perhaps that you could investigate, and then maybe come up with particular code that fits your application. Because we're always trying to build something new. In the systems area, we're always coming up with systems that solve a challenge in a different way, or something like this, to move forward. So the first few part of the slides here is really just sort of bringing everybody up to a kind of even, level, and saying that, when we're building, and all of these systems that Hadoop that we'll look at tomorrow in that are kind of built on this network stack, a communication stack, and it's all TCP/IP. There's an OSI model that kind of didn't take off, a way of describing the network layers and what happens, but we're very much concerned with TCP, UDP, the transport layer. All of our applications will be built on top of that. There's a bunch of things that happen under there, but we're really not concerned with what happens down here. This is all very much transparent to us. Our question really is, at the application level, do we use TCP, UDP, or some kind of messaging library that's already like a middleware that's built on top of that for us? Because as you'll see, just using TCP or UDP to communicate, transfer data between nodes in itself doesn't, there's a lot more to it than just say, let's use a TCP socket and let's transfer some data. You can really tune things and make things work a lot faster for you. And there are people that have done that and have built middleware that you can use, messaging middleware, I/O, high performance I/O type middleware for you. So, I mean, a lot about when we start working with Hadoop tomorrow, there's long lists of IP addresses of nodes. There's some of them, they're all in Australia. There'll be a bunch in Melbourne, a bunch in Perth, some in Tasmania, different places around Australia. Perhaps you do or don't know. But there'll be all of the nodes have IP addresses, and the IP address, along with the port number, identifies a process that you can send something to. So your node in your distributed storage system will generally have to have this kind of address with it in order to be part of the system. Your IP addresses can be static or dynamic, but mainly I think the distinction is that they can be public or private. So, for example, a typical cluster will have a bunch of nodes, and I've just put some dots here. There's some sort of high-speed communication network, and there'll be a main node that has a public IP address, and this will be the only node that you'll really be able to connect to in order to submit work to this cluster or store data on it or whatever. But this might be the case that all these nodes here you can't connect to directly. You can really only connect to this one main node, and then this one main node communicates to all the others, and then there's all this communication that takes place in here. That might be the case if it was like, these would all be private if it was like high performance computing. So typically a high performance computing center, you connect to one node that you submit jobs on and so on and so forth. But if it's a cloud computing application, so we do a lot of a data collection of social network data, and we have a bunch of nodes that run as a virtual cluster on the cloud. All of those nodes have public IP addresses, so any of them that we can connect to and with a desktop application and get data from. So and these nodes as well may well be able to connect to the internet. They might not. So if they're very well behind firewalls and so on, it really does depend a lot on the configurations of things and so on and so forth, how the cluster might look to you. But for our system that we show tomorrow, we'll be able to connect to all of the nodes, each one, log into it, see what data is on it or whatever like that. Now the terminology is as well kind of can change a little bit. So for Hadoop, this might be called like a rack. They give it a name as a rack, as a single set. And you can have all of these things geographically dispersed. So as I said, we'll have some kind of cluster in Melbourne and one in Perth and one in Tasmania, and there'll be some communication, and that communication typically happens over the public internet, right? It's going over, if these are independent clusters, then between them is the internet, and there'll be some sort of paths that they go through for the nodes here to communicate with nodes over here. If it's an organization that's providing you a generic cloud like Amazon, for example, they have different regions. So there's US, Ohio, and then the East Coast, I think. There's another one, and then Amazon can say you can put nodes in Sydney. They now have a spot. Amazon's moving to Australia, so they have a region in the Asia Pacific region there. So they have different regions, and if it's a company like that that's providing you with a like one single system, if you like, then they might have dedicated connections rather than just things going over, public internet type thing. They'll have maybe some dedicated connections that will increase the bandwidth between these kinds of regions and so on and so forth, right? So, I mean, again, what you see and what you get depends a lot on really what where you're getting the resources from, who's controlling the resources, how it's all being set up, and so forth. So there's two kind of ways that you can your nodes will be able to communicate with each other. Generally, if you're using TCP UDP, one is the TCP. It's a connection-oriented protocol. It establishes a connection from one node to the other. You then start sending data on the connection. You really see that as just a pipeline. You just start writing bytes, and the receiver is just receiving the bytes. And there needs to be some kind of additional protocol. You say, well, now when's the end of this is going to be? So we get a new line, or you write a line of bytes or something like that. Some sort of protocol above it, but it's what we call a connection-oriented protocol. And it's going to do a bunch of things, and I've got another slide that talks about it a bit later as well. But it's going to do some flow control, and the other, it's going to be reliable. In other words, you make a TCP connection, you start sending bytes, and either all the bytes get there in order, in exactly the same way that they were written, or you get an exception and something's gone wrong. Right? So TCP is going to provide some sort of reliability. The packets that get sent through the network, I don't really want to talk a lot about this, but there's a bunch of things that you need to put, that are put into the packet: a source port and a destination port, and sequence numbers and acknowledgement numbers and so on. But maybe I'll come back to this slide later, actually. So the other protocol, apart from the connection-oriented one, is the user datagram protocol, which is actually kind of what we call a best effort protocol. Your source node will just put data into a packet and just send it, and it's called best effort because the network does the minimum amount of effort to get it to the other side. And if it disappears, if it drops because a router has a full buffer or something like that, or there's an error or corruption, that's it. Nothing is done to fix it or to repair it in any way. Being best effort, it's quite quick. So with TCP, you have to sort of do some handshaking between the nodes, make a connection first, then you start sending data. But with UDP, the source node can just send some data immediately, put it in, send the data, and it's like sending a letter. You put the data in the letter and you put it in, and it eventually goes to the other side. And so there's no overheads in that way. But so it's used sometimes, say when you can tolerate some loss in the transmission of the data, so the packet might not get there. TCP is going to make sure that the data that you write does get to the other side, whereas UDP is going to kind of if it doesn't make it, you have to somehow, if you want it to be reliable, you have to build in a reliability protocol above. You have to have acknowledgements yourself or something like this. So it's used where you potentially you can tolerate some loss in the transmission. So for VoIP, for example, or transmitting something that you need real time, but where maybe some of the packets, if they're missing, it doesn't really matter because the other packets you can still reconstruct the missing data, or maybe if it's just a minor error in what's happening, it's okay. So where you can't tolerate loss, for example, and sorry, I still have very much a cold, but where you can't tolerate loss is if you're trying to transmit, say, a binary file, it's got to be exact. One bit of error somewhere, and you can't tolerate that. So in transferring of files and so on, you may well use TCP. So it's a bit of a comparison. There's no limit on data size that the applications can use This is addressed by TCP. UDP sort of has a fixed size. You can transmit lots of packets, but each packet you can only put so much in. In IP version 6, I think there's a concept of jumbo packet. The packet can get really big, but the bigger the packet gets, the more likely that it's not going to make it to the other side. So if you try to put more and more in, then yeah, if it makes it, you've transmitted more data in a single packet, but the probability of error goes up, and so there's kind of a you get an optimal setting at some point, right? TCP will go, and as I said, it will handle lost messages, but you won't get that in UDP. TCP provides flow control. So one of the things, and I'll show in the experiments that we'll do maybe after the break, is that with UDP, your data node might have a gigabit Ethernet card, and you think, well, the bandwidth of the node is a gigabit. Right, that's what it is. It's got a gigabit Ethernet card, so I can transmit a gigabit of data per second. Right, we say bandwidth bits per second, and you probably can. You can transmit with. You could start sending the data really quickly out of your data node, but the bandwidth is really a function of all of the nodes along the way that get to the destination. There's other nodes along the way, and there'll be bottlenecks, and the routers along the way that the packets are going between. So you won't really be able to transmit a gigabit per second. We'll try it. I'll show you the experiment of just pushing a lot of data out of the node, but then this data gets dropped and it just doesn't make it to the other side. So there's a kind of an effective bandwidth that you need to think about it. As well, if you're going over the public internet, you're competing with a lot of other flows of data from all different kinds of applications, other people on the internet. Now TCP will try to slowly increase until it gets to a point where it's using as much bandwidth as it can get from the network, that without going too far so that there's too much packet loss. So let's try to reach an optimal point, which is the flow control. And you can get, if you send UDP packets, these packets can arrive out of order. So if I send a packet A and then subsequently a packet B at the other at the receiver, that could receive B and then A. Right, so this is a real, out of order delivery. This could happen with UDP, and again, the experiment might show that after the break. We'll see, just run some commands and see if it happens. Maybe one or two packets will turn up like that, but TCP is providing always the bytes are in the same order that you sent. Most of the, like Hadoop uses TCP, it's not going to use UDP. I've always thought that building these kinds of systems would be interesting to consider how UDP can work, because if you've got you're regenerating codes and so on that you're using, potentially the loss of UDP packets you can build into the code in order that it can tolerate that for you. So instead of having an explicit error correction taking place in TCP, you kind of merge the coding theory layer with the UDP layer, with the transmission layer, so that you get a more effective code. This is kind of one thing that comes to mind. I guess there's people working in that space. So our socket is the sort of realization of this. So a socket is an API that's provided to you. You construct a socket at a server and at the client, the sender and the receiver, and they have a port number, and then on the socket you either send UDP packets or you make a TCP connection and send the data from one node to another. So there's a bunch of rules around that, how the socket works, but maybe you won't really talk too much about multiple processes can bound to one socket and this kind of thing and so on. What I wanted to get to was just a few things. So the bandwidth is the amount of data that can be transferred per unit time. You guys were talking about bandwidth is just the total amount of data, I think, in the slides before, but we always think about it as in terms of per unit time, so many bits per second. And the latency is the time for the packet to get from one host to another. It's typically a sum of propagation delay, the time to get for actually from one node to another, and then the queuing delay, so the time that a packet sits in a queue of a router and it gets through a queue and it transfers to another router, it sits in a queue and it goes through, and then the transmission delay, the actual bit rate of the line that it's being on, so you can kind of figure out latency. We'll do some measurements to look at latency. There's something called a bandwidth latency product, which is the amount of data that's in transit on the line at any one time between two nodes. TCP throughput limits, if we're typically using TCP, the throughput between two nodes is, there's an obvious limitation, which is there's some kind of bottleneck on there's some node along the path that's a slow node, and that'll be the bottleneck. It doesn't matter how fast the other routers are along the path between the two nodes, there'll be some sort of bottleneck. But besides that, there are some other bounds on throughput for TCP. So one is that the throughput is less than or equal to the receiver window size divided by the round trip time. Now these two things, the receiver window size is how much outstanding data does the receiver allow to have that it's acknowledging, in order to do the error correction. So that size divided by the time it takes for the acknowledgements to come back, or the round trip time, the time to the destination and the summer back. So this throughput is less than or equal to that. So you can kind of increase your window sizes, and we can see that in an experiment as well, increasing or changing the window size to try to increase the throughput of a TCP connection. There's also a theorem here that potentially we can look in the paper and see how it is shown that the throughput, now when you start getting packet loss and you start getting errors, you have a kind of bad network, then for moderate to high packet loss, the throughput is less than or equal to the maximum segment size, which is the amount of data that is sent, each time the TCP sends something. So you're writing bytes on TCP, but it's breaking it down into segments. And this is, sorry I didn't write this out as mass, but the maximum segment size divided by the round trip time times the square root of the packet loss probability. So if the packet loss probability was 0, the bottom line would be 0, and this thing would go off to infinity, and the bound doesn't really mean anything. It's just saying that the throughput is less than or equal to infinity, which is obviously true. But once you start getting some packet loss here, if the packet loss were 1, then you're back to a situation where the maximum throughput now is limited by the maximum segment size divided by the round trip time, which is just basically saying that because the packet loss is 1, meaning, let's say if it was 1, then it would mean there's no connection. Let's say it's really close to 1. If the packet loss is really close to 1, it means TCP has to send a segment and then kind of wait to see if it gets there or not, literally for every segment, because the packet loss is so high. So you're really only sending, the throughput is limited by sort of 1 segment per round trip time. That's what the throughput would be. Whatever the segment size is divided by the round trip time would give you the throughput under really high packet loss. So if the packet loss, as it goes down a bit, then you can have more outstanding segments, and so the throughput of the TCP can increase. So there's a couple of different bounds here, and it sort of depends on what's dominant. If packet loss becomes dominant, then the bound here may really be what's the bound that is you're limited by. So you can improve things by, you can scale the window size we talked about. You can have selective acknowledgements. There's another part of TCP protocol that does that, where you can just selectively acknowledge things that were an error. Timestamps on TCP can be used not just for the TCP protocol, but also for round trip time estimation, which is important for some of these things. And you can also, the message transfer unit is important as well. If it's too big, then what happens is you get fragmentation in the network, and things take longer. There's a whole heap of things that you can think about when just transferring data from one node to another using TCP. And people do this, and they provide libraries for you to use. And I'm not exactly sure. I'll have a look at what Hadoop. I was looking at it actually last night. What Hadoop is using for optimizing its transfer of data between nodes. So what I thought we would do today I'll just show quickly, but probably after the tea break, is so if you have the ping time on the network, and the ping time is the time it takes for a packet to get from one node to the other and back again, kind of round trip time, right? That's a very small packet, like a packet of minimum size, right? So that the size of the packet is not dominant. It's you just want to send a packet, and the receiver will send it back, as quickly as possible, right? So that ping time, let's just say it's ping AB between A and B. This could be considered a distance between these two nodes, and you might think that if the nodes are geographically further apart, then this distance might be, this ping time might be greater. And generally that does correlate. But does the triangle inequality hold on the internet with respect to this measurement? So the ping between two nodes A and C, is that always less than or equal to the ping between A and B plus the ping from B to C? Is a question that's been asked, so some research in that space, and is it true? I don't think it's true. It's kind of interesting. So we'll have a look at that. It's just a simple experiment. And then as well with the bandwidth. So if the bandwidth from A to B, if you measure how much packets you can send per second from one node A to another node B, if you then measure back the other way, is it the same or not in all cases? So we can look at this and just as some simple measurements and see after the break. There are some tools that we'll use to do it, iPerf and ping.